So it's 7:30 now for me. For you, it's 10:30. So let's start. And I see nothing on my screen, so let's adjust again. Ah, yeah. Now I have the full view. Can everybody hear me? Can everybody understand my accent? No? It's Westphalian German, so hopefully you will get used to it until the end of the presentation. So we'll be talking about Java library holes, allowing multi-platform denial of service scenarios, and I'm showing how to find entries in this language that show that this is an architecture that also has a lot of native stuff under the hood, and this native stuff can be abused or used or whatever in some means. So let's have a short view through the agenda. First, the motivation, why I did all this stuff, and then I go a little bit into the architecture. Then I show how to call all the native entry points and pass some parameters that are not very valid to that. Then I will give an overview how to find the vulnerable entry points in the GRE, and then I show how these can be, these results can be used to crash several GREs on multiple platforms and versions. Then I will show exclusively on Black Hat what I've sent to Sun last month, and this will be a public announcement. I waited for 4 weeks for them to answer, and I got no answer, and these are some nice entry points that are in the official language interface. So why do I do all this stuff? I'm doing my PhD thesis about security patterns and anti-patterns, and I've been doing previous work on bytecode engineering, which was presented in Las Vegas last August. And I also found out that in the Java environment, one important security anti-pattern is found, and that's the inadequate guarding of system layer functions against invalid values passed from the user level functions, maybe directly passed from CGI parameters or whatever. So, a little bit theory, only 2 slides. What is a security anti-pattern? A pattern is commonly used solution to a common problem, like Gamma and his friend said. So an anti-pattern is a commonly used poor solution to a common problem, and a security anti-pattern are commonly used poor solutions to common security problems. So that was the theory. Now I go into the practice, to our point of interest, the Java GRE, and it claims to be platform independent on multiple platforms. I saw it running on Windows and AIX and S390 and Linux and OS2. There are still some running installations running Java on OS2. Many banks, many financial institutions, they have a lot of OS2 legacy, my favorite operating system. So Java, like every language, has to communicate to the operating system, to the outer world, and therefore it needs sockets or higher communication like CORBA, needs files, database access, does compression, all these jar archives are compressed, needs graphic functions for the AWT toolkit or the swing toolkit, and uses, of course, for threading things like signals and threads. This functionality is realized via the platform dependent, realized via the Sun.dot classes, and the Sun.dot classes are our first point of interest. So this is the official picture from Sun, how they define their Java architecture. But if you do a little deeper view, if you take how the parameters are flow through the different interfaces, you see that all goes through JNI, and JNI is the main point of communications to the native layer. Therefore, all web start or AWT or the graphic functions or JDBC, the ODBC, JDBC bridge does JNI stuff, and the Java util functions does JNI stuff, and all goes through this interface. So, yeah, that's what I said. There are the Java classes which are in the rt.jar file, and the native code which which is located in the GRE bin DLL directory. And the dependencies can be inspected with, for example, with the depends.exe from the Microsoft SDK. So this is how the dependencies from the ODBC, JDBC bridge look like. You have here, for example, the bind column to exec, which is an export, and this export is mapped directly to a native Java function. We will see some more examples later. So the public API, what did I mean with this sentence? So let's skip the first sentence. It connects the Java code to the native code. That's the most important sentence on the slides, and allows native code. That's the way around the invocation interface to invoke, to start JVMs, and to run Java processes. But this is not topic of the speech. So people do a lot of errors. Why do they a lot of errors? Because the interfaces are designed to be used by experienced people, and therefore the entry level is very high. That's what Sun says in its tutorial about the JNI. So it's just the logical consequences that people, also the programs that some maybe do a lot of errors when they code with the JNI. So the JNI forms the OS abstraction layer, which is a set of Java class files, already said before, and it's coupled with the JNI and has the following shortcomings. There's no sandbox. There's no visibility protection. You can write to protected fields with JNI, and of course the JNI implementation is implemented with C, so you have a lot of error-prone code, pointers, character buffers, and memory allocation you have to do yourself, and can do the errors yourself. So and that's what's very dangerous, because native functions which are called with JNI, they do not always check the parameters correctly, if they are null values or large buffers or whatever. So, and in combination that they are, some of these functions are public, so available to the user code, at a very high risk to have maybe malicious code calling the native functions via or with invalid parameters, and so have some very bad impact on the JVM. So that's the introduction. So what does Sun says about its unsupported interface? The Sun packages are not part of the supported public interface, so therefore you shall not use the Sun classes to do something useful. But they also say that nothing prevents you from using it, so nothing prevents other people from using it. Maybe a security manager. But if a browser has not implemented a good security manager, so no one prevents someone writing some live connect stuff that crashes your JVM in your local machine by using the Sun classes. So what does the disclaimer not say? So there's no guarantee that the Sun classes are protected against invalid parameters, so you cannot be sure if they throw an exception and give you back control like it should be in Java, or they just crash the JVM. Sun implemented some basic check. So if you start your JVM with the xcheck JNI, you expect some protection against invalid parameters, but that does not always work as expected. And if you write programs using Reflection API, they can, even they do not call directly Sun classes, they can create Sun classes and invoke methods on them. So you have to be sure if you use Reflection that no one is passing values that cause your code to create Sun.star classes and invoke the vulnerable methods. So how is a typical exploit that I present typically running through the architecture? There's user code resisting in exploit.java and is calling some vulnerable function message utils to standard error, and it's passing a null value to it. And in the Sun implementation, there's some native declaration, and this native declaration, like we saw before, has a corresponding export entry in the Java DLL, Java Sun misc message util to string to standard error with the number 12, and that directly calls into the JVM. So there's no protection against this null value, and this null value is causing bad stuff in the JVM and is stopping it. This is some nice example, because there's another function which is just called ERR, and this is public and depends a carriage return to every string that is passed to it, and that calls the toStandard error. So why is toStandard error a public function? If they have a guarded function also in this library, but toStandard error can be called. So this is a code fragment that can be used to crash your implementation. And if this function wouldn't be public, there would be no harm. But this function is public, so it can crash. So passing, we have seen passing incorrect values from user code, like I will show that all later in some demo. Passing incorrect values from user code, like null pointers, they can provoke access violations and JVM stops in the native code, which is usable in some scenarios. For example, in browsers via applets or via JavaScript Live Connect, or in Java Web Start via malicious vulnerable applications, or if you can get access to the file system of a JSP engine, you can inject JSP pages that also have calls to these vulnerable functions and call this JSP and have the server stopped. but this is a rather difficult scenario. So how can these library holes be found? So again, when are they of good use for us? If they are, when are they of good use to, if they are reachable directly or indirectly from user code, if they have public access, if they have an object type, so if I can pass a null value to it. And it's even better if they are static, so I don't have to create an object so I just can call a function on the type and not on the object, which is a little bit easier to construct. So how do I find it? I've written a small tool, and basically what it does is finds the classes in a jar, like the RT jar in the Sun implementation that has native methods and constructors. And it tests all these classes if they have native methods and if they are public, and it's even better if they are static, like I said before. And it's checked if they have an object type, Java lang string, or a byte array. An uninitialized byte array is also very nice to pass to them. Or, yeah. And then I construct some code like we saw before. So this is the algorithm, some pseudocode. So all classes in RTJar and all methods and constructors are inspected. I have a for loop over the methods and constructors, and if there's an object type in the signature, I will inspect the method. If it's public, I will construct parameters corresponding to the signature, which can also be, again, but in very few cases, a recursive problem. And if M is static, I just have to call the function with the object type. And if it's not static, I have to create an object and call the method on this object with my constructed parameters. So if it's not public, I have to do something. I have to analyze the GREs, the source code maybe, which is also supplies from Sun in the source.zip, or I have to use my tool, which is JGrep, which inspects RTJar for calls to this function, or I use a wonderful JAD decompiler, which also can give me some nice information. So this is what I said before. So what does JGrep do? It analyzes if the non-public function can be called from some other function, so I can maybe do an indirect call to the vulnerable method through some intermediate methods. So this can be very recursive problem, but almost they are reachable via one level. So can also be very time consuming to write a Java program for every vulnerable or for every potential vulnerable entry. So I designed some tool to call the Sun, to call the vulnerable methods via some generic method, some generic approach via the reflection API. And the reflection API basically gives you the possibility to create objects of an unknown, or prior to execution unknown type, and execute methods on these objects or execute static methods on classes. So you just tell Java, create me an object of java.util.zip CRC or whatever, and it creates you some object, even if you don't import it from in your source code. So these reflection-based tools, they, like I said before, they do not explicitly import the Sun classes, but they create objects from the Sun classes and therefore should not be affected by the disclaimer and therefore should not crash and therefore should be correct Java code, but nevertheless, as intended, the tool does it. So what's the idea is dynamically create classes via the reflection API, then get the class of the vulnerable entry, then create an object via new instance, then you have an object of that type, then you get the methods, you get an array of the methods you can use, and if your method is in your candidate catalog, if it's a native function, you just invoke it and see what happens. So I found some functions that are vulnerable, and in the sun.classes, and these are the following: the span clip renderer, the message util, the signal, the buff image surface data, some unspellable stuff, some color CMM, and the Windows printer job and the path dasher are some examples which can be used to which are not very well protected. So the demo comes later. So also vulnerable was the following entry, and that was the Sun DCPR path dasher, and the Sun DC path dasher was available on all the platforms I have inspected, and inspected were Windows 2000, JDK 141, and the IBM JDK 131, distributed, for example, with Lotus Domino or distributed with IBM WebSphere, and the IBM JDK on AIX, and the Sun JDK on Solaris, Sun JDK on Linux, and the IBM JDK on Linux 390, and the IBM JDK on ZOS Unix system services. So let's step through the screens which I have taken from the crashes. So Solaris, Linux. This was not very verbose, just that segmentation fault on Linux 390. And this was very verbose on ZOS Unix system service, wrote me a 40 megabyte dump somewhere. So if I have someone can invoke this method several times, or the storage will be filled in just a short time. So I wrote the exploit once and crashed it on several OS systems, and I saw no platform surviving across multiple versions, across multiple vendors, and across multiple OS platforms. I haven't tested this on OS2 because I have no OS2 installation anymore available, but maybe someone who still has an OS2 version can try it. So let's have this was a client-side exploit. I also used it in Java server pages. And you can protect yourself against these vulnerable JSPs with the security option, and then some classes will be blocked from your Tomcat installation. So this is what happens when you use it without the security flag. You get a nice Java dump from the Tomcat installation. And if you have a minus security flag, everything is fine and you just get a 500 error and your server is still running. So there are some new vulnerabilities. The ones I reported to Sun last month, or this month on the 3rd of February, and the Jdbcodbc exploit, which is also very nice because many people use Jdbcodbc and maybe can fall into this somehow in this trap that is somewhere inside the Jdbcodbc classes. So to exploit this vulnerability, to get access to the vulnerable method, I had to build some infrastructure. I had to expose an inner class, and the inner class was the ODBC RP API object, and the ODBC RP object could be used to do some nice stuff. And yeah, the Jdbcodbc RP, it contained the Jdbcodbc driver, and that has a native library hole, but it was not public, so I had to export it somehow. And the ODBC, Jdbc, it had to be subclass to be somehow accessible. So I created my own object that extended the Jdbcodbc driver and just exported this this private element, and this private element then could be used to call this function export driver, and the export driver, which is the Jdbcodbc RP object, then could be used to call the SQL function, and the SQL function has a library hole, and the library hole straightforward ended into the JVM crash. And what is also not very nice, that the xcheck JNI parameter had no effect. It should somehow protect you against invalid parameters, but obviously it's not implemented in all calls to the JVM. Yeah, and these were all stuff that were in a unsupported interface of Sun, of Java, but there are also vulnerabilities in the official interface, and that's for example, in the Atlas 32 object, where you can create some overflow scenario, and the overflow leads to some JVM crash because there's a missing range check, and the missing range check, when you have the function, the update function in the checksum, in one of the or both checksum subtypes, yeah, you just read it from the source code that is supplied with the JVM, with the GRE, and you give a very high first value, which is an integer max value -3, or you give a length with 4. You have an additional result, or a sum that is negative, and this therefore leads to therefore the array index out of bounds exception is not thrown, and you directly go to the native function, the update bytes function, and the update byte function is then the end for this Java program, the unwanted end. Okay, there are some methods that are also buggy, and these were reported to Sun on 3rd of February. The Adler32 and the deflator set dictionary, the CRC update, the deflator, deflate, the checked import stream, the write method and the checked input stream, the read method, and all have the same pattern. They have an inadequate overflow handling, and therefore the insecurity is not supplied from you, it's supplied from Sun, and therefore the xcheck JNI does not help you. And basically, or forms an attack potential for browser or live connect stuff. Yeah, this can also be tested with an JSP, and even running with minus security. Of course, your java.util.zip class is trusted, and if it crashes, it crashes. And the Tomcat is dead also. Yeah, we've seen that before. Okay, the CRC 32 and the Adler stuff were very straightforward. The CRS, the checked input stream, I had to create an own input stream, which basically was used to bypass some check in the input stream. In the checked input stream there was a check, and that could be bypassed by returning some nice value, the max value -3, and then ended in an update call to Adler32. And then it crashed, like said before. So what can be, this is basically what's in the slide. What can be used for further reading. If you are interested in stuff that is related to Microsoft JVM, there was a great speech of LSD at Black Hat Asia. If you're more interested into bytecode engineering, I've made a speech at Black Hat USA in Las Vegas. That is also online on my website. And of course, if you find more overflow scenarios, you can, if you want to find them, you can look at the JDK sources, which is applied with every Sun implementation. So I will provide you with the tools. When I return to Germany, I will give them some more comments and have some more indents and whatever, so that they're usable. I will have them on my website. You can get JAD as part of Java C backwards, which is a nice decompiler set. If you're more interested into bytecode engineering, there's a nice API from Apache, and that's the BCL, which is formerly from the Technical University of Berlin, which was merged into the Jakarta Apache project. And if you want to analyze the the libraries and how they relate to each other, you can use, like I said before, the depends tool from Microsoft, or use some tool from the GNU tool suite. So let's have some demo. Or are there any questions before? No? Okay. So let's have some demo. What can I show? So the Nativefinder, we have basically seen the result of the Nativefinder. So let's have some look at the reflection invoker. And the reflection invoker basically is called, not the vulnerable cases are not called in a single Java program because it wouldn't run to the end if it crashed before. Therefore, I encapsulated it in a batch file or command file and have coded all the vulnerable cases into this batch file, and basically is a tool for me to try all the possible cases. So, oops. I called the batch file crash.4, crash14 cmd. So I have some old log files here. So it calls the first method, which crashes second. Actually, I messed around some of the parameter formats, so not every case runs through it. I have to fix that before I release the tool. But you see all these nice vulnerable points, they leave some trace, they leave some log files. And you only see three log files because some of the crashes, they create identical PID numbers. So if I would have some pause or whatever, wherever some takes this value from, it will create some more files. So, and I also have something for the IBM virtual machine. Which takes some more time, and is a little bit more verbose. And because it raises this nice message box, I just activated two cases. So the sun dumps, they show you where the process ended, and they show you the stack dump, the stack trace. They show you which DLLs were loaded, and that's it. The IBM dumps, they have a little bit more information about the internal state of the JVM. So, and what's interesting, of course, that it crashes on both implementations. So what else could I show? Yeah, genau. So we have some nice browsers here. For example, Netscape 7. And I've created some Live Connect CSC HTML. We can have a look on that. So this basically uses the Live Connect bridge between Java and JavaScript, and you can create Java objects within JavaScript, and therefore also call the vulnerable points, which then can be used to crash your client browser. So hopefully it works. So here's still my Netscape. It does a little bit. Starting the JVM takes a little time, and it's dead. So people which are not aware of that can be very bad surprised by that. So this is also, Opera is also not well protected against it. And of course the Internet Explorer using the Java plugin also is affected by it, but it cannot be crashed by the Live Connect stuff. But of course you can build applets and what did today happen? Oops. I have the CRC applet. The CRC applet basically is the same within an applet. Functionality encoded in the paint function. The paint function which is called to update the screen of an applet. So starting it should kill the browser in just a few seconds. So this one's gone too. So this is basically what is done with these two browsers. And there's also some problem with Opera, and I want to put it to the end, the Opera stuff, because my machine is always freezing when I'm running the Opera exploit. Therefore, we want to put it to the end. And where is it? It's here. So where's my Opera? Start with home page. So let's have a look at the source code of it. Whoops. Somewhere. No. Oops. So basically, what does it do? the Opera class libraries, they have a vulnerable function and the Opera plugin context. And the Opera plugin context, if feeded with the wrong values, causes the Opera to quit unwanted quit, sudden death sozusagen, and then the Opera dies very quickly. This would be a normal bug in normal installations, but in this case they also did not take very much care of their security manager settings. If they would have stop the access to Opera classes from user level, nothing would be harmed, but Opera classes can be used from user supplied or from applets user supplied code, and then as a logical consequence the Opera is killed. So where is it here? What's the Opera crash applet? So the Opera is also killed. And does my mouse still move? Write some more longer error protocol, but the JVM has aborted and my machine has also aborted, and therefore I want to stop this presentation now, and I'm open now for questions. Yeah, thank you. Yeah. So we are 8 people.